Hello, can you hear me? Hello, hello, can you hear me? Maybe I did. Hello, can you hear me now? Okay. Can someone say something? Yes. Okay. So we wait like 3 more minutes before we start. But do you have any question on the link list? Did you try to? Okay. So hello. So last time, like we had link list. So now my question for you, like, can question just in class question now. For can we perform? Can we sort the link list? Okay, good morning everyone. Let's start. Hello, hello. So now, my question for you everyone. So can we sort a linked list? Now, let's say we say we don't have a specific sorting algorithms, but now let's start with the sample sorting algorithms. Okay, so now my question, like, for purpose sort or insertion sort or selection sort, can we apply this basic sorting algorithm for linked list? Yes or no? The answer must be yes. Okay, so then if we say yes, is there any difference between sorting a linked list and sorting an array? For the items, the idea of the item is to bring the item like one by one to the final correct position. Let's say like we will bring the highest value to the first position, the largest number to the first position, and so forth. So the invariant for sorting items, no? And for linked list, that must be okay. That must be able to sort. We must be able to sort a linked list for sure. And now, when we analyze a linked list, a sorting items, we see that we have some operation on top of that. So what do we have? We have a select. Okay. We have a comparison. So we compare value between elements. Then we do the copy or we do the swapping. Okay. So now I will just need to use this one. Maybe I just put it in blank or in white. Okay. So I will draw white up. Okay. So now let's say we have a linked list like this one. We have a linked list. Okay. It could be say two doubly linked list or normal linked list, whatever. Okay. And now my question for you is, like, if I want to sort it using, say, when we need to sort it, then compare, it should be quite easy now. Compare, we have data field here, we have data over there somewhere. Okay, and now we want to compare. It should be able to do like a link dot data and then compare. That should be straightforward. And then we have another way is that we have the copy, which means we just copy the value from here to here. And now, if I ask you to think about the swapping, okay, what should we do? Let's say I have a bit more than that. Okay, I have here. If I want to swap these two values, this one, okay, I want to swap it. How can we do it? Let's say if you refer, you can have the linked list, you know. So now tell me, how can we swap it? What should we do in order to swap two elements in a linked list? This is just like an exercise, a small exercise for you. So what we do, we say swap link item 1 and link item 2. What should we do? We have the first and the last somewhere already. Okay, tell me what to do. So what should we do? You don't need to implement it now, but just tell me the way to do. This means we should everyone idea, just idea. The first solution should be we can always swap it by yeah, that is the thing. The first way is we change the link, and yeah, all the link related to this one we change to that, and then this one this change it's been it's linked this way, okay, and this way link back, okay, and of course we have to change this one link to this one, okay, this one change to this one. We can change the link, or there is good too, we can change the data field, everyone. No, we can change the data there, the data, you see, we can change the data. This means, so we have this, we can just change the value of the data field. No, is it possible? Of course. That will save us quite a lot of work. No, everyone got it? No? Now we can change it, just change the data. Okay, we swap it, means we swap the data, and that's it. That is the thing that I should I want you to remember, that okay, when we implement algorithms and we do many things, yeah, you will see, you find out that there's many yeah, in order to swap two links in the linked list, to sort them, we can always swap the value of the pointer. Again, cúp điện. No. Okay. Everyone, just 1 second, hold on. Everyone, can you hear me now? Is it okay? Yep. Sorry. Hello. So that is in the sorting algorithms, we can always we need to compare, we need to change, swap the items in the linked list in order to sort them, to move them to the correct position. So instead of just change all of the pointers related to one link, we can always change or swap the data inside that link, right? That is the idea. Everyone, is it clear one? Oh, yeah. Okay one, got it? The others, is it clear, everyone? Hello. Are you there? People, student. Hello, hello. Yeah, okay. So at least Quân do some reaction. Okay. Okay. So that is the message I want you to remember. Then now your task at home, I want you as a homework. Okay. So please try to do this one. Means implement basic sorting item on linked list. Okay. Apply the bubble sort, selection sort, insertion sort with linked list. Try to do it. Okay. Again, the task to practice. Okay. Now let's move on. So now we want to move to recursion. Okay. Okay, so it's good. Now, everyone, for recursion, what do we want? So recursion that you may know about that in the basic programming like C and C++. Okay, so we try to revise, let's say, review it for you, and then we try to show you some example that people use recursion and how to use it, and then we see we try to analyze and check the performance of the recursion. Okay, so the content would be introduction, some example, and then we have sorting algorithms using recursion. Okay, now for recursion, so recursion is what? Recursion is something that repeats itself. Okay, so in the function, when you have the function and inside that function it calls itself again, of course with different parameters, that we have a recursive method. Okay, so that will be the figure. You see that it could be like this, and say somehow this triangular numbers example is the way that people there is an example. It's mean the not the example, but this is the problem. They say they have a triangle that's formed this way. Means for this the first triangle will be 1. The second will be the first one plus one new column with the 2 items. The third will be the last. It's mean this one. Okay, plus 3. Okay, and then the 4 will be the 3 plus 4. Okay, so you see that the way that people define the triangular numbers, and you see that this is the example that we can say the definition of this triangle numbers is recursive, in a sense that so the current numbers will divide by the previous numbers. Okay, so that we say triangle number, and the way that we define, we use a recursive way to define it. Okay, that is the thing. And then you see that if people want to compute the number of square in that triangle, we can always do the for loop, no? Like we do like y is bigger than this. We do just add n to the total, so we have the result. And but we can think it as in a recursive way, means that instead of writing the for loop and while loop like this one, we just increase, and then total equal total plus n. We can always use a recursive method, say the triangle n equals n plus the triangle n minus 1. Okay, this means we call the function again with different value for the input. Okay, so that we say recursive. Of course, the incomplete version, we see why. And then for a complete version, a recursive for triangle would be like this one. So you see we have this one. We say if n is 1, we return 1. Otherwise, we return n minus n plus triangle of n minus 1. Okay. So here is the basic format of a triangle. It means that we have this one. We have two parts in a recursive method. We have name is the same here. Okay, and we have this part, we call it recursive part. It's been people ask us to do something like n. We try to solve it by using our algorithms or our function again with a different value for the input. Say we have n equals something plus n minus 1. So we step by step reduce the size of the problem we have to solve. From n we make it n minus 1 and so forth until the moment that we reach, we call it a base case. It means that is the moment that we can solve it directly without asking the function to, or without breaking it to a smaller problem. We say base case. So the base case here is n is equal 1. In that case, we don't have to do anything. We just know that the value is 1. Okay, so we have base case. Okay, and for a recursive, you see when we call the function, you see that say that we try to start with n equal 5. Okay, so we start here as 5 at as level 1. So when we say n equal 5, the system we try to do what? We try to call the function n equals 4, and after we get the result of that, we add 5. You see here. Finally, we add 5 to the result of the previous. This means not previous, the smaller n. Then we have 5 call 4. 4 we call 3. 3 we call 2. 2 is equal 1. In that moment, when we have the value, we will return. After we return, we can use that value is 1. We add 2 to that because from the output 2 here. We add 2 to that, we have 3. After we return 3, we get for version 3, we add 3 to that, we have 6. After we return 6, we add 4, we have 10. And after we return 10, we add 5, we have 15. Okay. You see that is the recursion. And there is one thing that you should remember is that here, when the system have to call recursive method, they cannot know the result of 5 directly. They have to wait. Okay, they have to wait there and wait for the result of triangle 4 in order to do the addition, add 5 to that. Okay, so in the memory of the system, actually they have to make a many version of the function. Means they have to make many version of the variable n. We have to store all of the statement and to know where should they return. So they say, okay, wait there until we have the result of the 4 and we'll get 5 to that. So you see that means if we call it 5 times, the system have to make 5 copies of the function. At least here we see they have 5 copies of the value n at the input parameters. Okay. For that reason, imagine if we had to call a recursive function with like they have to make like a 100 call or 1000 call. So the system have to make that many copy of the function and variables of that function in the memory. For that reason, recursion is not good in terms of performance, in time and in memory usage, both of them. Okay, both of them are not good in any sense. Okay, so do you agree with me now? Do you see why recursion is not good? Because we have to make a copy of the function, copy of the variables, and we have to keep track where to go back. So in many situations, the system will reject if we have too deep, like a recursion function like that. For that moment, now, if you agree that with me that recursion is not good, my question for you is, why do we need recursion? Can you tell me why do we need recursion? Everyone, any idea why you need recursion? It has to simplify the repeating task. It mean you mean simplify in terms of, say, the code, no? The code is that way. This means you see the code is quite like a small, short. Okay, we have smaller like a number of lines of code if we use recursion. But for the complexity of the problem, there is not always the case that recursions would be easier or like simpler than the others. Okay, of course, when you do exercise, you see that many is like a problem when you are forced to implement it in recursive way. It's not easy. Okay. Somehow, but it's not always the case that recursion is simpler than the others. Okay. For luận, there's some problem that easier to use recursion. Okay. That is agreement. And I would say that people always want to avoid recursion. Okay. And they will use recursion because they have to use it. Okay, they have to use it. Can you tell me, like, can you check and think on that? In which situation people have to use recursion? here. Yeah, they have some example like that. Okay, so do you see why is that? That is because from your example, that is because the solution we have at hand is defined using a recursive way. So they have recursive definition for the solution. Okay, it's been for a moment we don't know how to do it in a while loop and for loop format. Okay, so then for that case, it is easier for the user to write the code, to write the function in a recursive method. Okay, because it just directly translate from the solution and the algorithm you have at hand back to the code. For that moment, people will prefer to use recursive. Okay, but otherwise people don't want to do that, and you will see that later on for performance of the algorithms, people will try to remove recursion. That is the technique that we will try to do. Okay, so means that in general recursion is not good for complexity, not good for the in time complexity in time and complexity in the memory usage. Okay, people use it because they have no choice, or they just make it quick based on the available solution they have at hand without further investigation. Okay, so now I will try to show you some example if in your case. Okay, yeah, we have it this one for recursion. People will try to solve the bigger problem by try to break it to smaller problem. Okay, so we have it and we try to reduce the size of the input, say n, one step by step using recursion. Finally we reach the base case, and then we can finish. Okay, so you see recursion is not efficient in any way. Okay, so we have to store the address of the methods to remember. We have to store the argument. We have to do many things. Okay. Okay. So we have many great example of recursion. So you see that this guy example we can always do the while loop and for loop as before. You see, for I go from 1 to n, we just store it in the total and we multiply it again and again, so we can remove the recursion easily with the while loop and for loop. Okay, and now we have recursion. We put it in recursive format that will be like that. So you see we have to call function many times. We have to keep the copy of the variables everywhere. Okay, is that good? Okay. And you see here we have the binary search algorithms. Okay, one example, we see that here we have the low bound, upper bound, we search, we do many things, update with the normal while loop, and people can make a recursive version of that. Say we have the if else, and then if we do smaller, then we just do call the recursive again by update upper bound, lower bound. Okay, that is say exercise just to show you that we can always translate or say have two different versions of the algorithm using normal, we call it iterative version, and recursive version if we want. Okay. For the idea of the recursion, and we have this is a kind of a technique to solve a big problem. Means we try to say divide and conquer. Means instead of solving a big problem, we would try to break into two halves, like the way that we have in the binary searching. Okay, and then we call recursive methods based on that. That will help us to solve the smaller problem with that way. Okay, there is a few examples that is well known. There is one Tower of Hanoi example and the merge sort algorithms. If we are in class, I really love to ask you to play with the Tower of Hanoi game. Here always now like let's do it in here. So you see that for all of you, if you don't know about that, for who don't know about that, I here Tower of Hanoi. Okay, so we have here is the 3 columns of disk. Okay, we name it A, B, C, and the objective is to move this block from one column to another one. Let's say from here to here. Okay, and then you see that the rule for that is you can always only move one disk. Okay, let's say one disk on the top at a time, and we have to reserve the others. Mean this small disk must be on top of the bigger disk. We cannot put it in reverse order. Okay, so that is just the rule. Okay, and say here, let's say we have to move like a 4 disk like that. Okay, from the source here at A to C, destination. Okay, what is the algorithms people try to say is, in order to do that, what we want is where's my pointer? Okay, sorry. What we want to say here, move the n minus 1 disk to the intermediate. Okay, so that we can move the biggest disk here to the last to the destination. Okay, that is the way people try to solve, and then we have 2 steps like that. And the task we will be after that will be we bring the subtree, this one after it here, move this one to the destination. So we move the whole like a stack, a pile of disk from 1 to 4 to that destination. That is the algorithms. Okay, so you see we move this to B, and then this to B, and then from B we move 4 to C, and all of them to the top. Okay, that's the way we solve it. Okay, so now just to get you familiar with this algorithms or this game, so if you know a bit already, now I suggest that you do it. Okay, I suggest that you sorry, why I cannot so I suggest that you try to play this for me just at on your own. Means I want you to move the 4 numbers, let's say 4 3 2 1. Okay, instead of moving it to the last position, I want you to move that stack to this one, to the second column. Okay, so everyone, so please try at hand. It's when you can use number or put it in notepad. You do it step by step, or you can have piece of paper. You do it on your own, just to play with that puzzle. If you are new to that, or if you know it already, try to play it so that you see how it makes sense of the algorithm before we try to implement it. Okay, so everyone, please do it. Try to move that stack of disk from the first column to the second column using follow the rule of the Tower of Hanoi. Everyone, please do it. Okay. So everyone, is it okay? The others, can you do it? We do it in work maybe. So let's try to do it. So we have what? 1, 2, 3, 4. Okay. And second, have it insert table. Okay. Make it smaller. Okay, just 1 second. okay somehow. So what we have okay, so we have this. Okay, so here everyone, so have a look at that. So now if we want to move this one, so someone tell me what to do first. So the idea is we want to move all of this one to this one, okay? Oh, sorry, to this one. In order to move that, so we have to move the first two to this column, okay? And in order to move the first two to this column, so we have to move the number one to this column, okay? And then the second step, we what we have here. After that, we have what we have. We put this back, okay, and it's very strange. Okay, sorry. So we have this, and then after that we move 3 to the last position. We have this one, no? And next, what we do, we have what? We have 3 here, so we have move 1 here, okay, and 1 here. We move 2 to the position, and then that is, and then we have it, we put it here, okay. So you see that is the way to do. And after we have everyone to the last column, so we move 4 here, okay. After we have 4 here, the goal is to move all of this on top of 4, okay. So in order to move all this top of 4, so we have to move this one to this column, okay. And in order to do this column, so we have to move 1 to 4. That is the solution. And we have here, we have 1. You see here, that's 4. We have 2 here, 1. Okay. And after we have it, we have 2, 1, and 2. Okay, that is step by step what we try to solve it. And you see that we now very close to what we want. And then, so in order to move this, we have to move 1 to this position. And then after that, we have 2, and up. Lastly, we have 2 here and 1 here on top. You see that yeah, that is what we can do it. So you see we can just to summarize it, everyone. So you see here we move 1 here. The idea is we move the top. The goal is to have this one. This is the goal, okay. That is the important step that we may want to highlight. Okay, so you see from the beginning what we want to move our objects here to form this kind of thing, okay. In order to do this kind of thing, we have to ask ourselves how to move to first step and then last step, so we know what to do with one, okay. So you see that is the puzzle Hanoi Tower. So again here can you tell me like how many of you are very comfortable with that? Like if you are this puzzle. So tell me everyone please. Hello, please. Only two of you? And the others? The others? Is it too fast for you? And you are new, totally new to that game, to that puzzle? Okay. Okay. So do you? Okay, great. There's no problem. Okay, for sure. Okay. So do you think that you need like a more detail, like explanation of how we solve it manually? Okay. Need to do you need a detailed explanation? Detail or step by step explanation? Yes or no, everyone? Hello. Hello. Okay. So okay, so we the others. So why don't you say anything? Thank you, Yi. So the ideas of the algorithms, you know, like here is the home like process for the algorithms. Okay, means that we are trying to so we are trying to solve it, and here people show you one solution. Okay, so the solution is in order to move the tree in the up, where's my pointer? Sorry, is okay. So we want to move the whole stack of this from one column to another. Okay, because of the rule, we cannot move all of them in one shot like that. Okay, we have to plan it. Okay, and the solution is, in order to move one, we have to move the first subtree, and then after we can finally move it, we can move the last, pick it this to the destination we want. Okay, and then we move this one to this one again, and you see that this second step, this first step, we can repeat the solution again. Okay, so the solution for the first, in order to move this subtree to the second column, what to do? So we apply the same kind of solution. Means we say, in order to move the first tree stack, we have to move the first two, not to B, we have to move it to C. That is the algorithms. And after we move it, we can move 3 to B to form this subtree that we want. Okay, and we solve it recursively again. So in order to move 1 and 2 to C, we have to move 1 to B, and after that we can move 2 to C. You see that we apply the solution recursively so that we can move all of this to the destination. That is the idea. Okay, so we apply the solution again and again until we have a stack of this with the size equal to 1. That is the base case. From that, we can just move the disk. Okay, you got the way that we do. Okay, so I will try to put it like this. I will minimize it. Okay, so here, let's say here, is what we want. The idea, the first step we have say of this one, we want to say move the stack 1, 2, 3. Say the initial objective, move this one to from A to C. No, that is our first task, and the subtask of that is mean that one. If we want to move it, we have to move 1, 2, 3 from A to B. Okay, I want to put it like that. And okay, I'll make it like this for you too. Okay. And now our subtask of this, we have to move 1, 2, 3 from A to B. Okay. After we have it, we move the disk number 4. Okay, from from, okay, from A to C. Okay. You see the task, and after that we move. Finally, we move 1, 2, 3. We have it here from B to C. Okay, and that is the global algorithms. But this one is not doable because of the rule. Okay, so we have you know that it's not doable. So we have to make it, to break it down. So from here we have 1, 1, 1. Is that I'll try to make it smaller. Okay, so our task again is to move. In order to move 1, 2, 3 from A to B, we cannot move directly. We move the sub stack 1, 2. Okay, from what? From A. If you want, we have for A here, and we have move A to C. That is our task. I will try to make it easier for all of you see it. Okay. 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 And after we have it, this next step will be move 3 from A to B, no? And move the last one, we move 1, 2 from, because 1, 2 after the first step is in C, from C to what? To B. Okay. And now, is it clear up to this moment, everyone? The others. And now, and in here, for me, 1, 2 is not possible. We cannot move it. We have a subtask of that. Okay, so we have another kind of task behind that kind of thing. Okay, so the task is to move. If we want move 1, 2 to destination, our task is to okay. So we try to move 1 from what? From A. Okay. Because we want A to B. Okay. And after we have it, we move 2 from A to C. Okay. And last one, we move 1 from B back to what? We have A to C, so we have back to C. Okay, so you see that at this moment the step is doable. Okay, because we have the action for one object only. Okay, that is the way that people recursively apply the techniques. Go. Okay. You see that in here we have this one again. We have this step. Move to 1 to 2, 1 2 from C to B. Okay, and then we should break it into 2 steps again. Okay. Substat. So will be like move 1. Now we have from C back to A, and after we have it, we have move 2 from C again to the destination. Okay, and last one we move 1 from what? From A to B. Okay, so finally we have C, the whole stack. We want to see. Okay, from B to C, from C to B. Okay, so you see that is the way that people try to say solve the puzzle of Hanoi. Okay, so that is the step that we have to do it like step by step. So now I think that time for a break, but I want you just to practice. If you're not really comfortable with it, still not really comfortable with that, so now try to move it. Let's say we have the stack 1 2 3 4 again. Okay, I want you to move it from here. Okay, that is stack A, let's say. Stack A. Okay, stack A. I want you to move it to stack C. Okay, that just the very basic one. Or if you really want to play, you see that it's totally different. Okay, so I want you to move the whole stack from A to C. Okay, so everyone, so take a break, or if you're not really comfortable with that, so please try to do it in the break time. Okay, try to move it from A to C. Okay, everyone. Move from A to C. Tower. Let's say they use a tower. So it take a bit of time of you, but let's try to play with that. Everyone, okay? So to have that you get familiar with the way, and we can like do it without analyze the algorithm step by step in a piece of paper. Okay? So do the moving, like move the tower, and then okay. Everyone, so let's do it. Okay. Hello everyone. So welcome back. Are you there? Like when you are back? So, yep. Can you? Are you now a bit more familiar with the Tower of Hanoi Tower puzzle? Okay. So when you look at this, you somehow should be able to say what to do next. Okay. Okay. So now, what we want. What we want from this is, we say, you see that now, let's say if you still get trouble with the Tower of Hanoi, let's do it later, okay? So now, my question for you is, now if you have to write a function, okay, in order to solve the Tower of Hanoi, and if I ask you to do it in the iterative way, it means what to do in first step, second step, and the next step. I allow you to do if-else statement if you want, of course. While loop, for loop, whatever you want. Do you have any solution for that? Or is it easy? The thing is, it is not easy, no? Because we don't know. For this problem, we don't know the algorithms in iterative way. Okay? If I ask you to do what to do for a given input, we have no way that we can tell the program, it's been the system, how to do the if-else to move to the A, B, or C column. We don't know what to do. Okay, what we can do is just follow the solution in recursive way. Ask them to move the top to the B, and then move the fourth to the C, and then move the column here to the C. This is what we can do, no? And it's not easy and not straightforward for us to write an iterative like a solution for this puzzle. Okay, that is the problem. Okay, that is one concrete example why people say it is not easy to do it, and that is why people use recursion. Okay, everyone, is it clear? You see, that what we want to say. So for this specific application, recursive methods will be our final solution, because we don't know how to do it with for loop and while loop. Okay. Okay. So this is why people will use like recursion. You see, we have no other way to do. And now let's have a look at this one. Why can I do it? Oh, okay. So can you now check on the code, see what we have? So I would try to write again. So let's say from the beginning, we have the from, the B is the intermediate, okay, and the 2 is the C. Okay, so what people try to do now, people give us as a top n, and the number of this we want to move from the top. If the top element is one element only, okay, what we try to do, we just move it. Okay, we can bring out, say, please do it, because you have one disk only. What we can do is just move it without any concern. See? So if there's one disk, it is base case, so we can move it from here to here. Okay, so from A to here is C. This means we can directly move one disk from the source to the destination as we want. Now, if otherwise, if we have more than one disk, we cannot do it directly. What we say, now you see that we change. It is from, the first element is from, okay? So we say, we try to move it top n minus one disk from, okay? And the destination now, you see, the destination not this, is not the C not yet, like before, but we change the destination to B. No? And we will use C as the intermediate. Okay. So you see the three position of the do tower. The first one is from, second is intermediate, the last one with the destination. Okay. So you see that we change the order now. Okay. We swap this one, this one. This is what we know and what we have as the solution. No? We move top n minus one disk from the destination to the B. Okay. And after we have it, we move n is mean the biggest disk from the destination, like from the source A to the destination as we want, because you have one disk only. After that, we call the function to move again the intermediate B, okay, to the destination now will be C, and from A. So you got this solution implemented by recursive method. Okay. Everyone, is it clear for you? The others. Thank you, Yi, for reacting. Thank you. The other, please tell me. If you have problem, we have trouble with that, please ask question. Everyone else? The others? Hello. Okay, Bảo. Yeah, it's okay. On which part, Bảo? So now again, so let's say we now try to implement the function that solve the Tower of Hanoi. Okay, so we'll define this function do towers as a recursion in the recursive method. So we take three inputs. The first one is a from. The first one is the number of disks we want to have. Let's say we have the disk of 4 elements, and from the top we get 4. So the top n is mean from the top we count 4 disks. So we have the whole tower. Okay, and we have this one is the destination, is mean the current position, and this is the intermediate, just use, and this one is the last one, the destination. These are the source. So normally what we can imagine the from will be A. Okay, let's say we want the input at the beginning, we want to move 4 disks. Okay, from the top, the top 4 disks, from A move it to C. Okay, that's the way we name the parameters. And because the recursive method, we always have the base case. Okay, if we have 1 disk only, we can move it without any problem. No, so if 1 disk, we can just easily bring out this one is from here. If the input is like this one, we have A, and if we want to print out just from A, bring it to C, no problem, because we have 1 disk only. There's nothing to do with that. Okay, otherwise if we have more than one like disk, we cannot move it. Okay, we will use recursion. Here from the solution we have up the solution we have, we will move the top n-1. Okay, you see -1, that part -1 from the source. Okay, A, but we will not move that to the destination because we want to move the top 3, let's say input it 4, to the intermediate, now EB. Okay, and use C as the intermediate. Okay, now let's check this one. So the first one, the first step, the goal is to move 1, 2, 3, 4 from A to C. Okay, the solution is to move 1, 2, 3 from A to B first. Okay, now move 1, 2, 3 from A to B. Okay, that is the destination. Okay, and after we finish with that, we can move the last, it means is the top n, it means the biggest disk which we have at hand, from the source A to the destination, like this one. After we move it already, we can just move the disk number 4 to the column C. Okay, because they want this only. So we have it. And after that, we will move the top n-1. We temporarily put it in B. Now we move it from B, okay, the intermediate of the input here, to the destination. Okay, see here, after we have 4 in place, we will move the 3 first, the top 3 disks from B to C. That's what we want. The top 1 minus top n-1 from B to C. So that's it. And that is recursive, means we don't need to know what to do next. We just write like that. We represent the solution as a recursion. And then in turn, the do tower we'll repeat the process again, and let's just do it, break it down to smaller step as we do manually. And finally, if we reach the number of this to handle is 1, I can easily do it. Okay. Okay, everyone. Yeah. So everyone else, I hope that now is clear for you. So you see that in this case, the message is that when we have the solution at hand is in the recursive like a way, they were quite straightforward to define the function, to solve it, and that is just exactly what people tell us, and now we should just describe it using the function. Okay. Okay, in that case, the implementation will be like a straightforward, and that is why people use recursion. Means because we don't know what to do. Okay, we have no idea how to convert, how to move it, because we have no solution at hand. Okay. Okay, so that's it for one example, one application that we have. I mean, we are forced to use recursion. Okay. And now, if we clear on that, we now move to one another application. We call it merge sort. Okay. You will see either way people use recursion again in order to sort the objects. Okay. So have it. We have sample sorting algorithms. Okay. As we know, O(n) square. And now we have merge sort. There is one improvement. If we remember n versus log n, you see that log n is better. No? That is what? That is because when we compare linear check with, say, binary check, we see the difference. No? The log 2 of n is a lot better than n. Okay, so merge sort achieve that kind of complexity. Okay, now try to see what how they can do it. Okay, the idea for the merge sort is that we based on the example of the just 1 second, I check this one. We based on the idea that we have algorithms, but now we want to say if we have two sorted array, be able to sort them better and easier. I'm now checking my my lab, and you know that in one of the lab, I asked you to sort or to merge two sorted array. That is the lab number 1. Do you remember that lab? Everyone? Can you tell me how you let's say merge two sorted array? Do you remember that lab number 1? When you do the sort like that, when you do the merge like that, do you see any like a special properties of two sorted array when you merge them? Now, let's have a look at this. Everyone, do you remember that lab number 1, that exercise? Okay. So now, if we had two sorted array, if you have to merge them, what to do? What can we do? You see that if we merge in our sorted order, can someone briefly tell me how to merge them? And at the result, we have a sorted array again. What to do? We try to. Someone please. Tell me the idea of that. Means that we will use a pointer, no? We have two pointer, one for each array, and we try to compare between them. Say if it's 7, we compare with 23, and if 7 is smaller, we just copy it here, no? We put it number 1. Okay, and after we use it already, so we move our pointer to this. Okay, move our pointer to this position, and then we compare them again. So 23 and 14, we use 14 again, so we move the pointer to the next element. Okay, and now we have 23 and this number 39, so we use 23, so we move the pointer next here, no? So we have this one 47 and 39, we use this one, so we move our pointer here. Okay, and we compare again, so we have this is smaller, we use it, so we move our pointer here. Okay, and we have this two for 81 and 55, we use 55, so we move our pointer here and we compare again. Okay, then you see that now finally we will have all the value in place. Okay, and that will be in sorted order. Okay, for the final result when we merge them. Now my question for you, let's say we have here, let's say that is n1 and this m2 is the number of elements in our input. Okay, so we have n, let's say the total number of input, that will be n1 plus n2, no? Okay, so first of all, tell me the number of copy that we have to do in order to merge them and form a sorted array. How many items? How many copy that we have to do? How many copy do we have to do? Everyone? So if we copy to merge them to the array C, how many items we have to copy? We have to copy many times. Hello. Really? Okay. Copy the link. Copy the link. The link. The others. Can you hear me, everyone? Yeah. Yes. This meeting option. Up. What happened with your friends? Yeah, Microsoft did. No. Microsoft, I think, just changed the application somehow. Yeah, maybe Long. Hoàng Long. Okay, I try to like Phan Hoàng Long, add him to the meeting. No? Phan Long. Phan Hoàng Long are in the meeting already. No? It's French now. Okay. Anyway, back to this one, everyone. So everyone else, so please tell me. So, okay. So the others, tell me how many copy do you have to do in order to merge them? So we have only n copy, no? So we have this function. So we have the position, and we should say, we should compare it with the smallest number, or let's not the remaining numbers, and we should put it there. It's mean for each slot we copy only one time. Okay. Yeah, and for each loop we compare it one time, no? no trường because we don't know the position relation between numbers in the two array. Okay, they are sorted amongst them, but not among forcibly between two array. Yeah. Okay. But you see now, because we know that they sorted, the number of comparison is n, and the number of copy is only n. Okay, means that if we sorted, we don't need to do too many comparison. We don't need to do too many copy in order to put the item in the correct position. Okay, so we save something. Okay, so now based on that observation, so we have the sorted, the sorting algorithm using merge sort. We say merging. The idea is that now we try to divide the array into two every time. So divide and conquer. Okay, we divide into two every time we want to do. Okay, so up, what is it? Oh, nice. Oh, the first time I know it. I don't know how I make it. Up. Okay, it's nice that I can show the list of things in the same time by accident. Okay, anyway. So you see that now we want to do. We want to break our array into two parts. Let's say here, divide by 2. Okay, consider it is two sub-array to merge, but it is not doable yet. So we break into 2 again. And now at this moment, what is important is we have 2 sub-array, and each of them has only 1 element. We don't need to sort anything. We just do the swap or copy in order to put it in the right position. Okay. And now, after we swap these two, we finish with that. We put it in order. Okay. So this means we can sort the sub-array in just very basic step. Okay. And then we do it again. We sort them. Okay, and finally what we do the merge sort. Here we have two elements. Okay, so we have 2 sub-arrays sorted. Now we do the merge sort as we know. Put it here and put it here, put it here, put it here. Okay, so see that we use recursive function in order to perform the merge sort. Okay. Now let's look at that. So when we do it, the way we do is just say we have the sorting algorithms. We have the array. We have the upper bound, lower bound, just like in any array. So we have here, if you are the same, it means we have only 1 element, the lower bound equal the upper bound. Okay, and now if it's not, we get the middle. Okay, so we start to sort from the left to the mid, and another from the mid to the upper. Okay, and then we do the merge sort function. We call it again. After we call it, so we do what we say. We do the merge, which merge to array. So workspace. After we call merge socks here. We have two subarray in socket amongst them, and then we try to do the merge. Okay, so the merge is just the lower bow, and the mid is the lower bow in the left. The mid is the position of the first element of the right, and here the last element of the right. Okay, and you see how we do the merge. We do the merge is quite like as the way we do. We have the lower bow and upper bow, and sorry, the merge could be a bit longer than that. I will show you in the text box. But the idea is just we apply the algorithms step by step by breaking it into two elements, and that's it. Now let's check on the sorting algorithms. Okay. Just 1 second. I will try to show you the code for this. So, okay. And here the merge. Our low bow, and here we have the merge function. Sorry, just 1 second. I will put it here. I missed it last time. One second. Okay, it's exactly the merge function that you have in the lab. Okay, we have lower bow, upper bow, and then you see that we do the merge. If the lower bow is less than this, we do the we put the array lower bow into the workspace, and after we do all of the copy to the workspace. Okay, so we copy it back from the workspace back to the array. Okay, so you see that in this example, people use one extra like a memory. It means the workspace is the one that we just have us to store the data. Okay, and the array is the real value that we need to copy, and we compare. You see, we compare the array on the left and the array on the right, and then we do exactly as in the first lab. So we could be, if it's smaller, one of them y, or one of them if we is like we reach the end, we could be the on the remaining to the workspace. Okay, and after that we put everything back to the array. Okay, so that is what we have. Okay, so that is the merge sort, everyone. So now I really want you to just play with the sorting algorithms. Okay, now let's try to do it. Let's play with this. So try to have some value. Okay. So everyone, so let have a look at that. So please do the merge socks for that. Okay. 2, 4, 6, 8. Okay, so everyone, so try to do the merge socks for this data set, okay, and to see how people do it. The idea is just to break it into two and sock it again and again. Okay. So everyone, please do it. You will see what happened. Okay. So the merge method is this one. The merge method is exactly like the one you do with the lab. So you see that the merge method we have here, the array is the original array. Okay. The origin. The workspace is the one that you copy the value there. After you copy the value to the workspace, finally we copy it back. Okay. So everyone, so the idea is, can you finish the merge job? So when you do the merge, just try to look at this. This means the way that you break the array into two. Okay, you break the array into two, and then each time you break like that, you try to compare. Okay, and the key things for this algorithm is you reduce the number of comparison. Okay, so sometimes you, in order to find the position between two array, you don't have to compare this number to everyone else in the array, no? Like in selection sort, you have to compare everyone with each other so that you can know the position. But now, because it's sorted, you can reduce the number of sorts, and the number of copies, we reduce the number of copies in the sense that we don't need to say move it around. Of course, we have to copy into the workspace and copy it back to the original data. Okay, but anyways, so we can reduce the number of comparison. Okay, and that is the merge sort. Okay. In the textbook, they try to show you like the detail of number of comparison and the number of like copy in order to do the merge sort. Okay, then you will see what happened. But now, everyone else, can you finish the merge sort? Yeah. Mm-hmm. Thank you. Okay. So now, the others, please like when you finish the mark sort. The others, please like when you finish. Okay. Okay. So please like it and try to show you this one. The others, can you finish it? Okay. So now what I try to show you is that we try to show you the numbers like here. Why people say 80 n log n and log has been log 2 of n. So n log n actually here is the complexity of the items based on the say the number of copy that we have to make in this one. Let's say we have here an array of 8 elements, no? Array of 8 elements. Okay, and every time we divide by 2, we divide by 2 means the number of division that we have is log 2 of 8, no? Log 2 of 8 is the number of division. In the opposite ways, mean if we have 2 multiplied by, yeah, it's mean 8. At the top we have 8, we divide by 2, we have 4, we divide by 2 again, we have 2, and the last one we have 1, no? We don't need to divide anymore. So we have it. You see that, so we divide 3 times by, if we divide 8 3 times, so we get 1. That will be the value of the log, no? That is the meaning of the log. Log 2 of 8 means if we take 8, we divide by 2 3 times, we will reach number 1. That is the meaning of the log. Okay. So means that in this one we break into 3 parts. We have the first is 8 element here. Okay, and the second level we have 2 sub-array. Each array we have what? We have 4 elements. That is level 2. And the next we have 4 elements, 4 sub-array, each array of 2 elements. Okay, and each of them, when we do the merge sort, what does it mean by merge sort? In this case, when we look at the merge of the 2 sorted array, actually it's just a copy, no? So every time we see this number, we copy it here, copy it here. So we have 1 copy, copy it here, copy it here. We have 1 copy. So we have do it 8 times. We break into we divide by 2 3 times, and each of them we always have to go through all of the element 1. So that is 8 number of elements, and for each level we do the copy for element. So that will be n log n is the number of copy that we have met in order to sort the array. You see, because we divide by 2, we copy it to the workspace and back. No? We copy it to the workspace and back. All of the elements. No? Always have to go through the element at each level. So we have log 2 of 8 is mean the number of level we have to do. We have 3 levels. At each level we do a copy. So for all elements somehow. So here is the n, is number of elements. So log 2 of n is the number of level we have to break this array into the instrument divide by 2. Okay, and each of them we should do the copy. When you look at that, we don't have to copy many times, but for each level we copy each element only 1 time. It is different from the other sorting items like swapping and selection sort. We have to do a lot of copy or the comparison. And see the same for the number of comparison. For each level comparison, we don't need to compare all elements together, but we compare with, it depends on data, but we can save a lot of comparison because they are in a sorted order. Okay, so for that reason, the complexity of the merge sort is n log n. Okay, everyone, of course it's not very clear for all of you, but what I strongly suggest is that at home please read the explanation again in the textbook in page 292 or somewhere. Okay, around 292. It's mean okay, that will just give you a bit more detail on the comparison and the number of copy. But anyways, that is the complexity of the merge sorts. You see that in merge sorts, people try to optimize the number of copy and number of comparison in the same time. Okay, so that we say we have better sorting algorithm in that case. Okay, and of course one of the things that you should remember is that the merge sort need an extra space. Remember, for the last step, in order to merge 2 array this way, to 4 elements to array like that, merge them together, we need an extra space. So that is the important part, means the merge sort need an extra space, but that helps us to reduce the complexity. So depend on your situation, depend on your problem, whether or not you have enough space, and you can add extra space to reduce the complexity or not. Okay, so that is the thing. Okay, everyone. Is it clear? You should remember that most charts get better performance in time complexity, but it takes more space. Before we don't need any extra space in order to do that, but now we have it. Okay? Okay, is it clear, everyone? Hello. Okay, thank you. And then everyone, so there is one last thing I really want you to yeah, we have the detail. So the number of qubit here is the log n, and is the number of comparison at max. You see, we save a lot of comparison, min and max. Number of comparison is with respect to the size and things. But anyway, there is one thing that is very, very important, is that recursion is not inefficient, okay? And people have to use it, but later on, if we have time, people will optimize the algorithms to remove recursion. But there is one algorithms that have us to all way possible to reduce, it means remove the recursion, okay? That based on the stack. And I ask you to do it at the homework, and I will check it next time, okay? And I will check it next time. That's read about remove recursion with stack. Okay, and otherwise that's it for this section. Okay, everyone. Okay, everyone, do you have any other question for this? So otherwise, that's it for today. Thank you. Okay, otherwise, goodbye.